In this video, I would like to explain the second conductometry experiment. The aim of the experiment is to determine the solubility and solubility product of barium sulfate, lead sulfate at room temperature conductometrically to determine the solubility and solubility product of barium sulfate and lead sulfate at room temperature conductometrically. So let us see what is a solubility product. So solubility product, it is denoted by the symbol KSP. So solubility product, it is the product of activity of cations. It is the product of activity of the cations multiplied by activity of anions. So in a salt, cations and anions are present. For example, in barium sulfate, it is a sparingly soluble salt. Sparingly soluble salt means it is partly soluble. It is partly soluble. So it is dissociated to a very less extent and it gives cation, barium ions and sulfate ions. So solubility product, it is the product of activity of the barium ions and the activity of the sulfate ions. So in this experiment, we have to determine the solubility product of barium sulfate or lead sulfate, and using the solubility product, we can determine the solubility. So for barium sulfate, the solubility it is equal to, for barium sulfate solubility it is equal to under root of KSP, under root of KSP. Now, how the solubility product can be determined? So let us see the experimental part. By measuring the conductance of the solution, we can determine here the solubility product. So let us see the experimental part here. So the first part, it is the determination of the cell constant. This is the part first here, the determination of the cell constant. In the previous video already we has been discussed how to determine the cell constant. So to determine the cell constant, we require the zero point 0.1 normal KCl solution. So we have to measure the conductance of 0.1 normal KCl solution. Okay, and with the help of that, we can determine the cell constant here. Now the second part, it is the determination of solubility product. Now in this case, you can see here determination of the solubility product of the sparingly soluble salt. So the conductance of conductivity water. So in this experiment, we have to measure first the conductance of conductivity water. So the water we are using to prepare the solution of the barium sulfate. So we have to measure the conductance of that water also. It is LW. Then the specific conductance of that conductivity water, it is denoted by the letter KW here. So specific conductance, it is equal to conductance multiplied by the cell constant. Then the equivalent conductance at infinite dilution for barium sulfate, it is given. That value, it is 143.5. Similarly, the equivalent conductance at infinite dilution for lead sulfate, it is given. It is another sparingly soluble salt. So its equivalent conductance, it is around 149.5. The unit of the equivalent conductance, it is Siemens centimeter square per equivalent. Now we have given the two salts here, barium sulfate or lead sulfate. So first of all, let us see the barium sulfate. So in this experiment, we have to prepare the solution of the barium sulfate. The sparingly soluble salt, barium sulfate, actually it is not soluble in water, so we get the turbid solution. So we prepare the solution of the barium sulfate, then it is filtered, and we have to take here the filtered barium sulfate solution. Okay, we have to take the filtered barium sulfate solution, and we can measure the conductance of that filtered barium sulfate solution. So in the first column, the conductance it is given here. Then with the help of the conductance, we can determine the specific conductance. Once again, specific conductance it is equal to conductance multiplied by cell constant. Conductance multiplied by cell constant here. Then the specific conductance of the salt. So specific conductance of the salt it is equal to uh, the specific conductance of the salt it is equal to K of the salt it is equal to the specific conductance of the solution minus specific conductance of the water. If the water shows some conductance, then we have to subtract that value from this here. Actually, in many cases, it has been found that water generally shows the zero conductance. But if anyhow water shows the specific water shows the conductance, then we have to calculate the specific conductance of the water, and we have to subtract the specific conductance of the water from the conductance of the solution. So conductance of the salt, that is barium sulfate, it is equal to specific conductance of the salt it is equal to this Ks minus Kw. This is Ks minus Kw here. It is Ks minus Kw here. This is Ks. Okay. This is Ks here. Ks minus Kw. Okay. Then solubility. Solubility S it is equal to 1000 into K of the salt divided by equivalent conductance at infinite dilution, and finally solubility product. So in this way we can determine here the solubility product of the sparingly soluble salt. So this is the calculation part is given here. Solubility of barium sulfate in gram per equivalent, gram equivalent per decimeter cube it is given here. So we are getting the solubility here we using this formula, using this equation, and gram per decimeter cube we can use this formula here, equivalent weight of barium sulfate it should be multiplied here. So in this way we can determine the solubility of the barium sulfate, and that is our aim, to determine the solubility of the barium sulfate. Similarly, we can determine the solubility of the solubility product of the barium sulfate. So you can see here the solubility product of the barium sulfate it is Ksp. So this is the dissociation of the barium sulfate. So K it is equal to concentration of this multiplied by concentration of sulfate ion divided by the concentration of the barium sulfate. So it is equal to, so Ksp it is equal to concentration of the barium 2 plus ion into concentration of the sulfate minus ion. Okay, so as the solution contain equal number of both the ions and concentration of the ions equal to the solubility of the salt, so we can write here the solubility product of the barium sulfate Ksp it is equal to S square. So in this way we can determine the solubility product Ksp it is equal to S square here, or S it is equal to under root of Ksp. Okay, so thus we can determine here the solubility product as well as the solubility of the barium sulfate. So this is our second experiment, determination of the solubility product of the barium sulfate or lead sulfate using conductometry. By measuring the conductance of that solution we can determine the solubility product of the sparing